Physics part 311. So I've been giving you the values for different planets in the solar system, and now I provide you t square divided by r cubic year square per m power raised to minus 3. The constant for all of these values is 10 power raised to minus 25. Say for instance for Mercury it is 2.99 into 10 power raised to minus 25. For Venus, it is 3.00 into 10 power raised to minus 25. So as 10 power raised to minus 25 is a constant, I just give you the values for all these planets. So let me get along with the values. For Mercury, it is 2.99. For Venus, it is 3.00. For Earth, it is 2.96. For Mars, it is 2.98. For Jupiter, it is 3.01. For Saturn, it is 2.98. For Uranus, again, it's 2.98. For Neptune, it is 2.99. And for Pluto, it is again 2.99. So we get an average of 2.99 into 10 power raised to minus 25. Satellites are widely used in telecommunication. Many communication satellites are placed in what is called geostationary orbit. That is, they are in an equatorial orbit with exactly the same period of rotation as that of the Earth and move in the same direction as the Earth so that they are always above the same point on the equator. Details of the orbit of such satellites are worked out in example which follows. We've got an example here for a geostationary satellite. Calculate the height above the Earth's surface, calculate the speed in the orbit. Radius Earth is equal to 6.38 into 10 power raised to 6 m. Mass of the Earth is 5.98 into 10 power raised to 24 kilogram. Now it's your turn. The radius of the Moon is orbit 3.84 into 10 power raised to 8 meter, and its period is 27.4 days. Use Kepler's law to calculate the period of the orbits of a satellite obtaining the Earth just above the Earth's surface. Radius of the Earth is 6.38, 10 power raised to 6 m. Communication satellites are considered in the upcoming section. Weightlessness. Suppose that you are carrying out an experiment involving the use of Newton balance in a lift. When the lift is stationary, an object of mass 10 kilograms suspended from the balance will give a weight reading of 10 gram per Newton. If the lift accelerates upwards, the acceleration is 0.1 gram. The reading on the balance increases to 11 gram per Newton. If the lift accelerates downward with acceleration of 0.1 gram, the apparent weight of the object decreases to 9 gram per Newton. If by an unfortunate accident the lift cable were to break and there were no safety restraints, the lift would accelerate downwards with an acceleration of g. The reading on the Newton balance would be 0. If during the fall you were to drop a pencil with which you are recording the balance readings, it would not fall to the floor of the lift but remain stationary with respect to you. Both you and the pencil are in free fall. You are experiencing weightlessness. The figure illustrates your predicament. It might be more correct to refer to the situation as an apparent weightlessness, as you can only be truly weightless in the absence of a gravitational field, that is, at an infinite distance from the Earth or any other attracting object. A similar situation arises in a satellite orbiting Earth. The force of gravity, which provides the centripetal force, is causing the body to fall out of its expected straight line path. People and objects inside the satellite are experiencing a free fall situation and apparent weightlessness.